Thank you, Kelly, and good morning or good afternoon to everybody who's listening, and welcome to my small workshop regarding spread spectrum techniques and how to reduce effectively EMI with that. So here's my small agenda for my session for today. So first of all, we're going to have a quick look into the spectrum of a traditional switch mode power supply. So this is really rough and short, out of the box thinking, how does a switch mode power supply spectrum will look like. After this, we'll jump in the theory of frequency spread spectrum. And then if the theory is done, I'm gonna show you some practical measurements on real boards and how these practical measurements will also be shown on the EMI receiver. After that, I'm gonna have a quick look into the limitation of frequency spectrum, because nothing is for free, so everything which has a benefit will also have a limitation. After that, I'm going to conclude it, and then if we still have time left, we continue to our question and answer session. So just up front, whenever during my session I will talk about frequency spread spectrum, I will sometimes use the phrase FSS. It's just frequency spread spectrum, and this makes just life easier for me to explain something to you, as well as I'm talking about switch mode power supplies, sometimes will use the phrase SMPS. So everywhere where we have switch mode power supply, SMPS is the phrase of frequency spread spectrum, FSS is the phrase. So before jumping into the theory, short outlook, who I am, who your presenter is today. So as I already said, my name is Florian. I'm 30 years old, and I live in a very small village inside the middle of nowhere in the middle of Germany. So I just put in red arrow where I live. So there's no big town nearby, so I can't tell you I live nearby Munich or Berlin, for example. Just put the red arrow here. So this is where I live. I'm married. I'm a field applications engineer at SMPS, and I have one son and one small Dalmatian dog you can see here. But now let's jump into the session why we are here. So first of all, let's check how a spectrum of a traditional switch mode power supply will look like. To show it to you, I did the following experiment. So I took an evaluation board of a standard off-battery buck controller, the EVQ4430. This is just a 3 amp buck controller. You can directly connect it to a car battery, and the output voltage is something between the input voltage and down to 1 volt with a maximum output current of 3.5 amps. To show you the spectrum of the switch mode power supply, I just connected, maybe you can see it here, a small pin to the switch node. So actually I connected it to the inductor, which is connected to the switch node, to record directly the switch node with an oscilloscope. To show you the different influences, I added a trim frequency potentiometer, you can see here. And this is just a potentiometer which is connected between the frequency pin and ground. And on that table, you will see using a 250 kilo ohm potentiometer allows me to trim the frequency of that SMPS between 350 kilohertz up to 2.5 megahertz. I added a second potentiometer, which makes me able to trim the duty cycle. And as a SMPS in general is not able to trim the duty cycle, I just used a small trick. So I used this potentiometer to replace the bottom resistor of the feedback network. So at the end, when I'm trimming the duty cycle, I just change the output voltage. And looking into that table here, I replaced resistor 8 with a 20 kilo ohm potentiometer, which allows me to change the output voltage between 2.5 volts up to 12 volts. So this was my measurement setup, really basic measurement setup. I used my computer to do some recording. I used the Rohde & Schwarz MXO series to do a real-time FFT measurement on the switch node. Here is a laboratory power supply, and here's our MPS efficiency meter, which I just used to have a load on the SMPS. So first of all, looking into the really basic spectrum of the SMPS. So my operating point was easy. It was 13.5 volts input voltage, 5 volts output voltage. Switching frequency was 500 kilohertz, output voltage 1 amp. So this makes our mode in the continuous conduction mode. And the resolution bandwidth of my FFT was 9 kilohertz. And this is the result. So on the top, you see the switch node with the duty cycle corresponding to V in and V out. And on the bottom, you will see the real-time FFT the oscilloscope did for me on the switch node. And what we can see, we see the switching frequency, we see all the harmonics, the 10th, the 20th, the 30th, all the harmonics. So up to 30 megahertz. After this, I increased my frequency span up to 300 megahertz, as you can see here. And what you can see is that the spectral power of the switch node will decrease with the frequency. Here at higher frequencies, you can see the noise floor of the oscilloscope. In fact, this picture looks the same for every SMPS you will measure. The only difference is the area where will you reach the noise floor. So in general, the spectral power will decrease over the frequency and will reach the noise floor something between 300 megahertz and 700 megahertz, always depending on your switching frequency and on the EMI design of your IC itself. So now in the second stage, let's explore what the different parameters will do to our spectrum. Therefore, I changed the input voltage, I changed the duty cycle, and I changed the switching frequency. And here I have provided some small videos for you. So on this video, what you can see is here, it's the switch node again on the top, and on the bottom side, there is the spectrum. I just draw that blue line in here, so you have a reference. I was starting with an input voltage of 13.5 volt, which you can see here on the bottom. And here the switch node you will see will change the duty cycle by increasing the input voltage. And now you can see what's happening to the spectrum. So here on the bottom at the blue arrow, you will see I'm increasing the input voltage. On the top at the blue arrow, you can see the duty cycle is changing as well as the input voltage is changing. And what you can see in the spectrum is that the effective EMI, so each peak of the spectrum will be increased. And the reason why this is because we are measuring the emissions on the switch node, and the input voltage is directly linked to the hot loop of the buck SMPS. This means here effectively the switching flanks are higher because now we are switching between, for example, 0 and 27 volts instead of switching between 0 and 13 volts, which leads to an increase of the EMI. In the next step, I changed the duty cycle, which just means that I changed the DC output voltage of the SMPS. And here we need to take care what happens at these specific harmonics. So I will try to stop the video. So in fact, what you can see here, changing the duty cycle on the bottom with the blue arrow, you can see increasing the duty cycle will not affect the spectrum at all. However, there is one specific phenomenon, and I'm going to show it to you now. This is exactly at 50% duty cycle. You can see that all even harmonics will disappear, where the odd harmonics will still remain the same. This is really specific for 50% duty cycle and really specific for this one operating point. If I'm continue the video now, you will see that already for 51 or 52% of duty cycle, the even harmonics will be back in the spectrum, as you can see here. So at the end, I said I changed the switching frequency of the SMPS. Problem here is when I touched the potentiometer on the frequency pin, you will see that I added some noise to my spectrum. So in this video, we should maybe focus on the first few harmonics here on the bottom left side. I again started at 500 kilohertz and increased the switching frequency up to 2 megahertz. And what happens, you can see here. Here you can see the noise which I just injected during my body, touching the frequency pin. However, I increase the switching frequency and all these peaks will move far away from each other. What you can also see in this video is that each specific peak itself will remain the same in height. But that's just to look like an electrical engineer, I would say, will look to these peaks. However, if an EMC engineer will look to that video, he will look different to that, because in the EMC world, we are not looking at spikes. No EMC engineer in the world is saying, hey, the second or the third or the fifth harmonic has this value. No, an EMC engineer will focus on a frequency in the spectrum. And for example, just gonna take the pen, he's looking at 4.5 megahertz of switching frequency. And as you can see, starting again from 500 kilohertz, just looking at that frequency, I would say that our spectral power at 4.5 megahertz is something around 8 dB. Now, when I increase the switching frequency, just will increase the video to the 2 megahertz and try to stop it, you will see when the EMC engineer will look at exactly the same frequency, he will now see that the emissions at that frequency, I would say, is round about at 20 dB. And so this is the two different looks. So each specific peak will remain the same in height. However, if you look at the exact same frequency, your spectral power of the switch node will be increased. You will see that, just need to erase all ink, again on the next page. So here I draw a line. This is my bottom line for an EMC engineer. This is the spectral power of my SMPS. And now I'm going to change again my switching frequency beginning at 500 kilohertz. I will change it to 2 megahertz. And you will see that the spectrum of this will be increased. So we will be way above the blue line in the whole frequency area. So just need to check. Okay, now the video is finished. And now what you can see is that we are above the line, checking the left side again, round about 12 dB. So why is this the case? It's easy. An increase of the frequency. So let's say, for example, here, we double the frequency from 500 kilohertz to 1 megahertz. This means we have twice as much switching flanks. Let's just imagine we are having the green frame now. This means at 500 kilohertz, we have 2 switching flanks in this green frame. So doubling the frequency to 1 megahertz means we have twice as much switching flanks in this green frame. As you can see, we have 4 switching flanks. However, the energy of these switching flanks will be transferred to only half of the peaks during the FFT in the frequency area. And this means doubling the frequency will increase your spectrum of your SMPS by 6 dB. And this is exactly what we saw in the video before. I changed the switching frequency from 500 kilohertz to 2 megahertz. This means 2 times doubling of the frequency. And this was exactly that 12 dB more in the spectrum. So what's now the theory behind frequency spread spectrum? So this is exactly the technique we want to use now to reduce that spectrum. First of all, to understand how frequency spread spectrum works, we have to look at a block diagram of a really old EMI measurement receiver. There on the left side, we have the antenna, we have the pre-selector, first mixer, filter, second mixer, filters, demodulation, and the display. The thing is, the second filter here, this is the resolution bandwidth filter. After the resolution bandwidth filter, the demodulator will create a power out of our signal, and this power will be directly displayed at your display, which you can see. So this means after the demodulator, because then our signal was transferred to a power, we have no chance to influence our spectrum anymore. However, the first mixer most of the time defines my frequency span, which is predefined. So the only possibility to reduce the spectrum by not reducing the spectrum of the SMPS, but of the measurement, is to adapt the resolution bandwidth filter. And the resolution bandwidth filter is given by the bandwidth. The bandwidth is given by the lower band edge and the upper band edge, which is defined by the -3 dB, as well as the filter order. And there, checking EMC standards, most of the time as an EMC engineer, you will have 3 resolution bandwidths. This means most of the time it's 9 kilohertz for frequency ranges up to 30 megahertz. The resolution bandwidth is most of the time 120 kilohertz for the mid-frequency ranges between 30 megahertz and 1 gigahertz. And above 1 gigahertz, most of the time the resolution bandwidth can go up to 1 megahertz. And what this EMI receiver does, if we take a really, really old school EMI receiver, no fancy FFT receivers, is the the measurement receiver will just sweep through the predefined frequency span, and wherever the switching frequency will create a peak into that spectrum, the display of your measurement receiver will directly show this peak surrounded by the resolution bandwidth. And this will exactly look like this. So we have a switching frequency with all the harmonics, and with the resolution bandwidth we have here, it's displayed on your display of your measurement receiver. This does also mean if you increase your resolution bandwidth, the gaps between your switching frequency will become smaller, and the display will show a broader area, which directly defines the resolution bandwidth filter. And here, this is what you can see in green. So in between of these peaks, this is empty area. And this area, this is exactly what we want to use to hide the energy of these peaks, or at the end to reduce the size of this peak. But the only way to do this, we need to move energy from this peak inside this resolution bandwidth filter into the green area. And what you can also see is that with a higher resolution bandwidth, the green area in between these peaks will become smaller. This means the possibility we have to reduce the EMI is smaller with a higher resolution bandwidth. In the next step, I also considered the switching frequency of the SMPS. So if you have a really slow switching frequency with your SMPS, you will see that your harmonics are much nearer together than with a higher switching frequency. This will also effectively reduce the green area, which reduces the possibility of hiding energy into that area. So in theory, the best way what we can do, and this would probably be the best way to have a frequency spread spectrum, is to move all of the energy we have in these peaks into the green area, which will result in a perfect white noise. So even if that is impossible to move the energy to a perfect white noise, even this is limited. So if we would be able to move all the energy from these areas, which is inside the resolution bandwidth filter, to the green area, that we have a perfectly flat spectrum, our absolute maximum attenuation, which is possible using spread spectrum, is given by 10 times the logarithmus of the resolution bandwidth divided by the switching frequency. And this is something you can see here on the right table. You can see that if the switching frequency of your SMPS is smaller than your resolution bandwidth, your attenuation will be 0, for sure, because your resolution bandwidth here, this means the blue area, if this is bigger than the peaks are together, you will have 0 attenuation. In the same time, going back to my example from the beginning, if we take a 500 kilohertz switching SMPS with a 9 kilohertz resolution bandwidth, the maximum attenuation we can achieve is 17.4 dB. If you go to higher frequency areas and increase the resolution bandwidth to 120 kilohertz, your effective attenuation which you maximum can achieve is 6 to 2 dBs. So, but how to convert now these peaks to a perfect white noise, or at least into a frequency spread spectrum signal, because to transfer it to a perfect white noise is slightly impossible. The answer is easy. To convert this peak to a frequency spread spectrum signal, we need to dither with the frequency around the center frequency. So this means for SMPS, it's easy. We have a switching frequency, and this switching frequency needs to move around the center frequency. For example, if we have here our example again from the beginning, if we have 500 kilohertz here, we need to move with the switching frequency, for example, between 400 and 600 kilohertz. But how does this dithering affect our original or our spectrum? To explain that, I'm going to show two cases. So let's begin with the first case on the left side here. So for example, this case is FSS is too slow. So you can see it here. This is our fundamental frequency, and this moves very, very slow within this bandwidth. The problem is the EMI measurement receiver has a settling time. So if this error moves too slow, this means if it stays inside this bandwidth longer than the settling time of the filter, our effective attenuation with frequency spread spectrum will be 0. The second case is our amplitude is too small. This is exactly what I described before. So if my center frequency and the movement around the center frequency is too small, and we will stay all the time inside this resolution bandwidth filter, also the effective attenuation will be 0. Even if we move fast, we will never reach the edge of the filter. We will always stay inside, and the EMI measurement receiver will show us the full value of the peaks. So first of all, let's once again go back to the case 1. So I told you we have a settling time. So this settling time of this resolution bandwidth filter, it's physically given. So the settling time of a bandpass filter is 1 divided by the resolution bandwidth. This means we have to move through the resolution bandwidth faster than the settling time. Now let's take back our 3 filters again. For a 9 kilohertz filter, the settling time is 111 microseconds. This means if this little error moves from the lower to the upper band edge, it must be faster than 111 microseconds. So, which is quite fair. The problem you will see here. So if you have a resolution bandwidth, for example, with 120 kilohertz, the settling time is 8 microseconds. So now we have to move from the lower band edge to the upper band edge within 8 microseconds. The problem is it's not just the reduced time, also the bandwidth was increased. And if we have a resolution bandwidth of 1 megahertz, we have to move through an area which is 1 megahertz big faster than a microsecond, which can be really tough in regards of a hardware design. So this means for us to have an effective attenuation on the frequency spread spectrum, our frequency change must be faster than the resolution bandwidth of the filter by square. So looking back to the picture, if we have a 9 kilohertz resolution bandwidth in our EMI receiver, we need to move through that 9 kilohertz bandwidth in 111 microseconds. This is quite fair. This makes us to a change of the frequency of 81 megahertz per second. I tried to show you how fast we already need to be if we have a 120 kilohertz bandwidth, because the area from the lower to the upper bandwidth is more than 10 times higher and the time is more than 10 times slower. We need to move a lot faster through this bandwidth to have an effective attenuation, which leads to 14 gigahertz per second already. And for the 1 megahertz resolution bandwidth filter, I did not even try to make a GIF because my desktop was too small, but this would result into 1 terahertz per second of frequency change. And what do we do if we change the frequency around its original frequency? At the end, it's just frequency modulation, what we do. So now we should let the power designers pass by and think with the brain of a communications electronical designer. So now we have a frequency modulation. A frequency modulation is generally given by 2 values. The first is the modulation frequency. And the modulation frequency is just the frequency how often we move through that band pass within 1 second. So if I'm gonna let the arrow move again, the modulation frequency, if we would count how often this arrow would move through that bandpass filter, within 1 second, this is exactly our modulation frequency. And the second, how to define a frequency modulation, is the modulation depth. And the modulation depth is just the minimum frequency that arrow will reach here, and the maximum frequency, which the arrow will reach here. So it's the delta frequency, which is given by the maximum minus the minimum frequency. And having that modulation frequency as well as the modulation depth, we can create a modulation index. And the modulation index is just given by the modulation depth divided by the modulation frequency. So at the end, the modulation index will just describe the spread of the frequency, so the maximum divided by the minimum frequency, so the frequency this arrow will pass, divided by how often it goes through that within 1 second. Why I'm going to tell you that is because if we have the modulation index, it is easy to see how we can reduce our peaks in the spectrum by using the Bessel functions of the first kind. Here on that graph on the right, you can see that in the black line, we have our fundamental frequency, and all the other lines are the sidebands. This means if we have deactivated our spread spectrum, this means our modulation index will be 0. And all the power of this peak is in its original peak. This means the 0 sideband, this means the original carrier frequency is here with the value of 1. If we now activate our spread spectrum, this means our modulation index will be greater than 1. You will see that power from this black line is transferred to all the sidebands. For example, to the first sideband in the red, to the second in the yellow, to the third in the green, and so on. And the higher this modulation frequency will become, you will see the smaller all these Bessel functions will become. So in general, we can see that the higher the modulation index will become, the smaller the peaks of our spread spectrum will become. What we can also see is that there are some modulation index, for example, 2.4 or 5.6, where the fundamental frequency will be 0. This means that our carrier frequency in this specific operating point will be 0, and all the power will be transferred to the sidebands. So now, as I said, the modulation index, as bigger this will become, as more attenuation will get. Why just don't we make this modulation index going to infinity? Because we have two limitations, two physical limitations. The first thing to make the modulation index big is to make the delta frequency big. The problem is we can't go to infinity, because imagine a 500 kilohertz switching SMPS, you cannot change the frequency by 2 megahertz. Because if you have 500 kilohertz moving around by 2 megahertz, this would result in negative frequencies, which is just impossible. And the other thing is we could decrease the modulation frequency. This means if we move slower, means less often through the middle of this bandpass filter, this will increase our modulation index. However, the physical limitation is here. If this modulation frequency will become too small, then we are violating the settling time criteria of the bandwidth filter. So this means if we move too slow, we will stay too long inside the bandwidth filter, and then our attenuation will also become zero. And this is most of the time the problem every spread spectrum has, that you need to find really the sweet spot of your modulation index. However, it has also something good. So the thing is, if we adapt frequency spread spectrum, for example, again to a switching frequency, we will always adapt this to the switching frequency. This means to the original switching frequency. So let's take this example. We have a frequency modulation of 10 kilohertz and a modulation depth of 10 kilohertz. This modulation depth will be injected to the fundamental frequency of our SMPS. And this results in the fact that for each harmonic, the modulation depth will be twice as high, 3 times as high, x times as high, which you can see in that GIF. Because if I move the fundamental frequency, for example, from 400 to 600 kilohertz, my second harmonic will automatically move from 800 kilohertz to 1.2 megahertz. So this means the modulation depth will become high for high harmonics. And this will automatically have a high modulation index, which is good for us, which makes our frequency spread spectrum very effective for higher harmonics. Now we have, now as we know how and how fast to move this error, we need to know the waveform, because we now know that we have to move through this bandwidth filter really fast, and we know that we have to move far away from the edges of the bandwidth filter to achieve a good attenuation. However, we still don't know the waveform, how to move around. And therefore, I would introduce you some waveforms. So in theory, the best thing is if we move through that frequency span with a constant frequency change. So this can, for example, be done with a triangular waveform. You can see here on the left side, we have our minimum frequency and we have our maximum frequency. This means this is our modulation depth. And here we have our frequency of this triangular waveform, which is then nothing else than our modulation frequency. The problem you can see here, if you use a triangular waveform to implement your frequency spread spectrum to your SMPS, you will have a delta frequency, so a change in the frequency within a specific time during the slope. However, if you're on the edge of this slope, this frequency change will only be half during that time. And this makes the triangular waveform suboptimal for attenuation on the edges. If you want to have a constant frequency change over time, for example, then you can imagine having a sawtooth ramp form. As you can see, during the rising slope, at each slope, we will have a constant frequency change within a specific amount of time. And then if we are on the top edge, we will directly jump to the bottom edge. So this means we will directly jump from the maximum to the minimum frequency within one switching cycle and then repeat the same again. The problem is this huge change of the frequency here, it nearly goes to infinity. Looking into it as an SMPS designer means this frequency change will happen within one switching cycle. And this can lead to big problems of your SMPS control loop. Considering this, there are mixing products, for example, the Hershey Kiss, where the slope at the edges is much sharper than during the middle edge, or you have a step triangular waveform where the frequency change here is much smaller. So from a stability point of view at your SMPS, it's much easier to deal with that. And in addition to that, in new SMPS generations, like for example the MPQ4371, there's also the possibility that we can adapt a dual frequency spread spectrum. And what this means, you can see here. On the bottom side, I have recorded the waveform in blue of the spread spectrum. And what you can see here, it's a triangular waveform with a 15 kilohertz. And on top of that, there's an additional 120 kilohertz modulation. So with these parts, we can add 2 modulation frequencies into the spread spectrum modulation. So why do we need to do this? This is something we can find out here. So I did some practical measurements with the frequency spread spectrum on a real SMPS. So what I did now, I once again took my carrier frequency with 500 kilohertz, and my frequency span was 20% of this 500 kilohertz, which is, as a rule of thumb, a quite good value if you start developing and using spread spectrum. This will result in a frequency hub of 100 kilohertz. This means I'm changing my frequency, my fundamental frequency, between 450 and 550 kilohertz. Now what I did in this video, we will watch the video soon, is I'm sweeping the modulation frequency from 120 kilohertz to 2 kilohertz with a triangular waveform. When I now start the video, you can watch here to the spectrum. So here in yellow, you can see my 500 kilohertz switching frequency displayed with the resolution bandwidth of the filter I used. Here on the top, in the pink line, you will see my spread spectrum signal, where you have on the x-axis the modulation frequency, and on the y-axis the modulation depth. Now, if I start a video, you will see that at the beginning, as soon as I start spread spectrum, I will directly have an influence of my spectrum. So you can see here, I'm moving energy from this peak to the sidebands. This is exactly what we are doing. So here we have now our fundamental frequency in the middle. Here we have the sidebands, and here this is my my spread spectrum with 120 kilohertz. Continuing to watch the video, I will decrease the modulation frequency, which automatically results in a rise of the modulation depth here. You can see it here. So what we are doing, going to pause the video once again. If you're looking at the modulation index, your delta F here is increased. However, your FM, your modulation frequency, is also decreased. So in fact, the modulation index should slightly be all the time the same. It's not fully linear, so it's slightly moving, but it's most of the time in the same area. However, you will see here in the spectrum that there is a sweet spot where we can achieve up to 10 dB of attenuation. And by the rule of thumb, you can say the best attenuation you can achieve with spread spectrum is when your modulation frequency is absolutely equal to your resolution bandwidth filter. And this is the case now. So I finished the video here. So I ended with a modulation frequency of 9 kilohertz with a resolution bandwidth of 9 kilohertz, which you can see here. And I achieved the attenuation of round about 10 dB. So how does this affect my whole spectrum? You can see here. So starting again, same conditions. I just increased my frequency span here up to 30 megahertz. And as you can see, as soon as I will start the spread spectrum, which I'm doing now, you will see that I directly get an attenuation. So here, looking the pink line again, high modulation frequency, I still get some sort of modulation. What we can also see here for the fundamental frequency on the left for the first, second, and third harmonics, my attenuation is very low because my modulation index is very low. For higher frequencies, the attenuation is better because we automatically get a good modulation index for higher frequencies. And now to show that the attenuation is best when the modulation frequency is close to the resolution bandwidth, I'm going to continue decreasing my modulation frequency, and you will see that I will achieve more and more attenuation in the full frequency band. This is again here, I'm going to pause here. This is the sweet spot. This is the maximum attenuation we are possible to get with this settings here on the top. So, but this was now at the moment just a practical measurement with the scope. How does this influence my EMI receiver? So these are measurements taken inside our MPS EMC chamber with our Rode and Schwarz measurement receiver. So we just did the same exercise again. My carrier frequency was once again 500 kilohertz. My modulation depth was once again 100 kilohertz. Modulation waveform was triangle. And now I started with a modulation frequency of 9 kilohertz. And the resolution bandwidth filter you can see here was also 9 kilohertz. On the left picture, you can see the spectrum of my SMPS without, and on the right side with FSS. And then I just put some markers here. So the first marker and the second marker, you will see that I get an attenuation from the left to the right side of about 10 to 20 dB. Now on the next slide, I just did the same exercise again with a higher frequency band. I once again used a modulation frequency of 9 kilohertz, but in this frequency band, my resolution bandwidth was 100 kilohertz. So you see, I'm still getting an attenuation of 5 to 10 dBs, but I'm out of that sweet spot where my modulation frequency is slightly the same as my resolution bandwidth. So I increased my modulation frequency once again and took the same picture. And as you can see, now I can have an attenuation of 10 up to 20 dBs. So this means if I'm just jumping back and we are just looking at these numbers here on the bottom right side, we have with a 9 kilohertz modulation frequency minus 77 dBm. And if I just change the modulation frequency to 120 kilohertz, we have minus 80 dBm. This means by just changing the modulation frequency, I gained 3 dB of EMI emissions. And that's why we implement in our future products always the dual spread spectrum with the 15 kilohertz and the 120 kilohertz. So we will be able to support the best possible attenuation in each frequency band. And this is what you can exactly see on this scope. So here in green, we see that evaluation board without spread spectrum. In blue, it's a dual spread spectrum with 10% of span. And in orange, we can see the dual spread spectrum with 15 kilohertz and 120 kilohertz. You can see for sure in the low frequency area, the single spread spectrum works better. And why does it work better? Because simply the span is bigger. This means just through that span, we have a bigger modulation index, which leads to better EMI performance. However, you will see that even the dual spread spectrum will have an attenuation greater than 10 dB at each spike. But now if we look at a broader frequency area, especially now checking the radio band, the FM radio band, we see that the dual spread spectrum will gain us about 3 to 4 dB more attenuation in that frequency band, just by having this 120 kilohertz frequency spread spectrum part. So now let's just quickly jump into the limitations of spread spectrum. So because now we say everything is fine with spread spectrum. No, it isn't, because you need to know what frequency spread spectrum does. Because it's exactly that. We do not damp each peak, we just move the energy from each peak of the SMPS to the area between the resolution bandwidth filters. And this is what happens to a specific frequency band. Here I just took an FM radio tuner. You want to listen to a FM radio frequency, something maybe 102 megahertz. And here on the left side, I don't have spread spectrum active. This means my harmonics are outside of my radio band. I can listen into radio, everything is fine. When I turn the modulation on, I take the energy of these peaks and move it to the red area, which means I don't have any radio anymore because my noise will be higher, so no chance to have the radio anymore. And the second limitation, spread spectrum will always add a ripple to the output voltage. This means here I took an evaluation board and measured the output voltage ripple in correlation with my frequency spread spectrum. As you can see, the spread spectrum was always the same, and the output voltage ripple can be tuned by tuning the inductor and the output capacitor values. However, even with the absolute optimum setting, which we can achieve, it's not possible to make the spread spectrum fully flat on the output line. You will always have an influence on your output voltage. So at the end of my workshop, I'm going to tell you how to implement frequency spread spectrum, because now we know everything about spread spectrum. We know the benefits, we know the limitation, but how to use it as an electrical engineer. The first and easiest thing is you just buy an SMPS that has spread spectrum already implemented. For example, 4320, 4340 series. New series from MPS also allows you the possibility to play around with the modulation depth as well as the modulation frequencies. So in new generations of SMPS, you will be able to select the most fitting spread spectrum for your purpose. However, sometimes you have an SMPS already in your design and you are close to go into serious production, and now you're just failing the EMC. And now it's not possible maybe to change the SMPS anymore, or there's just no time. And now I'm gonna show you a small trick how to add frequency spread spectrum to every SMPS which has a frequency pin. I took again the 4430. So the 4430 is a buck converter which has a frequency pin, as you can see here. So if you have a buck converter with a frequency pin, you just have to measure the voltage on that frequency pin during normal operation, which is in my case 480 millivolt. And to that frequency pin, I want to have a modulation depth of 20%, which will result in a voltage change on the frequency pin of plus minus 60 millivolts. So what I did, I used a timer IC and implemented a pulse width modulation onto that frequency pin, which shifts my frequency voltage from 480 millivolts plus minus 60 millivolts. And how to do that? It's easy. First of all, you have your timer IC with your output. You have a DC blocking cap, and then you have a resistor, and then you have a second resistor with a capacitor. So now how to calculate this? As a rule of thumb, you have two possibilities. The first is looking at that network. The first assumption is the resistance of your capacitor is way much lower than the resistor of R2. So all the current will flow into that capacitor. So having a given value of R2 and my modulation frequency as well as my delta voltage I want to achieve, I can just quickly calculate my resistance of the capacitor, which gives me a capacitor value of around about 170 nanofarad. So I select 100 nanofarad. So the second assumption I'm doing is that the first resistor, resistor 1, is way much bigger than these two resistors. So this defines the main current going into the circuit. And doing this math, I calculated resistor 1 is around about 11 kilohertz, so I selected 10 kilohertz. And what I did here now is to take the measurement with exactly that values. I took 10 kilohertz here, 1 kilohertz here, 100 nanofarad here. And what you can see is on exactly that point, beginning of the filter, I have my perfect PWM from my timer IC. And here, this is my voltage I'm adding to that frequency pin. And this will exactly result in the spread spectrum, in a triangular waveform of the spread spectrum I have told you above. So at the end, to conclude, frequency spread spectrum does have many benefits and can effectively hide EMI emissions of your design in unused areas. Please be aware that FSS can only hide EMC and not reduce the effective EMC. So this means we always take power from the peaks and hide it in the area in between. We will not decrease the overall power which is emitted from our SMPS. FSS cannot truly reduce EMI emissions of the design. We just move it into the neighborhood where we just reduce the peaks and move the energy to other frequency areas. Please be careful when using frequency spread spectrum in a specific frequency area. In example, the radio band, because you will have maybe other frequency bands you are now blocking with the energy you move from the peaks away. And depending on the values of your external components, for example, the inductor or the output capacitor, you may add a huge voltage ripple on your output. And now I'm coming to the end of my presentation and starting with the Q&A sessions. Thank you very much for your attention.
Thank you, Florian. Lots of good info today. Just to let everyone know, there have been questions. We are recording this session, and we do have the presentation will be available. We will email that out to you all by the end of the week. And you can always look for our past efforts at monolithicpower.com/webinars. We did go a little long on that one, so we have 5 minutes, and we're going to start promptly with our next one in 5 minutes, but we do have a bunch of questions. So we're just going to try and dive into them. If we don't get through them all, maybe we'll send out an email or something with the remaining questions. The first one, I don't know if this one was really about the presentation, but what's a good cheap probe to use with the tiny SA to find RFI?
Oh, a cheap probe to find RFI. It's easy. It's not part of that webinar. You can look into our old webinars. One of our first webinars we did from MPS was exactly that. And there the engineer just used an MLCC output cap, which was soldered to a BCI cable. So just check our webinar for the first EMI webinars there. You will find it there. You will see how to use it and how to use an MLCC with a specific size on a BNC cable to look for EMI.
Next up, when I enable spread spectrum on my PMIC, I start seeing tones on my sampled signals through the mixer circuit. How do I solve this issue?
This is a really good question. I'm not 100% sure if I got it right. If you say you receive a tone, if you mean a tone with an audible noise, you can just increase your modulation frequency. And that's mainly the reason we from MPS use slightly higher modulation frequencies than the resolution bandwidth to do not have an audible noise on our SMPSs. So if you have an audible noise, most of the time your modulation frequency is too low. So you have that huge output ripple on your V outline, which will result in your MLCCs creating a tone. If you mean a tone like distortion, that's what I mentioned. You can fine-tune your network consisting of the inductor and your MLCCs. More MLCCs, smaller inductor will result in less output ripple, which will help even with an audible noise or with distortions on the output.
Great. Next up, what is the influence of the GND cable on the oscilloscope probe? Shouldn't this be as short as possible?
Absolutely. I absolutely agree. I think you are referring to my picture from the beginning. I just took this one because I measured very, very low frequencies with the frequency area to 30 megahertz. And I directly measured the switch node. So the voltage on my probe was plus the input voltage to 0, so 13 volts. And in that case, the distortion through that ground line was minor. So in fact, if I would want to measure it very correctly, the ground loop of the oscilloscope probe should be as small as possible. That's correct.
And then another oscilloscope, using a ground spring on the oscilloscope probe would reduce the parasitic inductance and probably increase the measurement accuracy.
That's exactly what I mentioned. So this is the best way to measure this. As I mentioned, I put this small pin to the switch node, so I measure the switch node directly with my videos. So I did not measure the real EMI output, so I measure the switch node, so the EMI emissions of the full switch node. So therefore, the ground did not play the huge role. In this case, if you really want to measure the emissions of the IC, the ground plays a huge role, and therefore you should try to increase the loop with the ground spring to a minimum. Sometimes even this ground spring loop is too big, and then you have to use something else like active probes.
Next, what is the significance of different resolution bandwidth per different frequency range?
I'm sorry, can you repeat the question again?
What is the significance of different resolution bandwidths for different frequency range?
Oh, I just took that out of the standards. So I'm not an expert when it comes to standards, but most of the time the standards will refer to this resolution bandwidths for this frequency area. In fact, at a measurement receiver, you can use any resolution bandwidth with any frequency area. I just used the most popular ones from the standard.
Great. Thanks. And then I apologize to everyone else who's asked questions, but I do want to keep us on schedule. I think, Florian, I think we're going to have to, all these questions are recorded, so maybe we can send out an email with that we can help try and address all these good questions that everyone had.